Good morning, everybody. It's Friday. It's Hawaiian Shirt Day. All right, I know through the years my students have asked many times, Mr. Bruin, what do you look like with hair? And the answer, of course, is not very impressive. Oh, there's nothing's growing up top. All right, let's get started. We're continuing to cover mechanics and motion in particular. Today we're going to start with graphs. I'm going to break this into several parts so it doesn't get too long. You can watch them at your leisure. We're going to start with just the graphs themselves, then we'll do some examples in the next part, and then we'll move on from there. All right, here we go. So this slide is getting more and more complicated. We've already covered dot diagrams or motion diagrams. Remember, we're covering just one-dimensional motion. That's it. And remember, in one-dimensional motion, we have three major types of motion. We have constant position, where the object's at rest. We have constant velocity, where the object is moving at a constant rate, but not changing direction, one-dimensional. And we have constant acceleration. We've already covered dot diagrams, and last video covered kinematics equations. So now we're covering graphs. We're covering xt, or position time graphs, vt, velocity time graphs, and at, acceleration time graphs. Now remember, we are covering these graphs simply for these three types of motion. On the AP test, that's going to be 90% or more, or 100 up to 100%. Of all the different types of motions we'll ever see. Things that get more complicated than that are covered in Physics C with calculus. So here we go. What do they look like? So constant position, or something at rest. The position is constant, x is constant, the velocity is 0, and the acceleration is 0, so the graph is ridiculously easy. We have a constant position, we have a velocity that's 0, and acceleration that's 0. All right, for constant velocity, the velocity is constant, the acceleration is still 0, and now x graph gets more complicated. It's linear. So we have a linear graph here. Velocity will be constant, and acceleration is 0. Our most complicated graph of the batch is our constant acceleration graph, in which the acceleration, of course, is constant, so we see that over here. Our velocity becomes linear, and our position graph becomes parabolic. Now, for those of you that are taking calculus, you will know why this occurs, because you have learned about differentiation and integration, and you'll see why this has to be in this order. For those of us that are not in calculus yet, it's no big deal. All you have to do is understand the relationship of the graphs. Now, to get information from the graphs, what do the slope and area mean for each graph? So I've got a little table over here. For a position time graph, the slope means the velocity. The area under the graph doesn't really mean anything. For a velocity time graph, this is the one that you're likely to see on the test more than the others, because it contains more information. You can look at the graph, read the graph, and find the velocity. You can look at the slope, and that tells you the acceleration. You can find the area under the graph, and that'll give you the displacement. And then there's acceleration time graphs, which the slope is a new term, which we don't study in Physics 1. It's called jerk. But that's beyond the scope of this class, so it's not listed. And then the area under the graph tells you how much your velocity changed, so delta V. All right, so let's end that, and let's go to our paper and talk about a few things, and then we'll look at some simulations. Okay, so it goes like this. So here is the same thing that you just saw in the PowerPoint. All right. And let's see, the position time graph, when you're at rest, notice that it's really simple. This spot right here, what do these graphs tell us? All right. This spot right here, the intercept, on the x, t, or the position time graph? That tells us where we start. So that's our starting position. So that's our starting position right there. Okay, how do we tell how fast we're going on this graph? So the slope right here, and I always encourage students to draw this little triangle thing. It helps you remember how to take the slope. You take it, the rise over the run, and also it tells the person grading your test, the reader, that you know what you're talking about, and you're trying to find the slope. So the slope tells us how fast. Okay, how fast we're going, and it also tells us what direction. Okay, how fast and in what direction? Because if we were going, if the slope was this way, say down this direction, then we'd have a negative slope. So that's a negative velocity. The one that's shown here is a positive velocity. All right, piece of cake. That tells us what direction. So right here we can see, how do we find the slope on this graph? Well, it's a little more complicated, but you just draw a tangent line. Let me do that with a different color. So right here we see that we have a fast velocity because we have a high slope. Right here we have a smaller slope, and right here we have a velocity of 0 at the beginning. So we start with a 0 velocity, then the velocity gets larger and larger. So we're speeding up. So this is a positive acceleration. Whenever it's curving or parabolic upward, we have a positive acceleration. If, on the other hand, we had a curve that was, say, downward, so some kind of slope like this, then this would represent a negative acceleration. So on a position time graph, when you have a curved line, you're accelerating. On a position time graph, when it's linear, you have a constant velocity, no acceleration. So on this one, you can see the acceleration is 0. Okay, and on this one, the acceleration by default is also 0. All right? Okay, let's take a look at our velocity time graph. What does this graph tell us? Okay, so this spot right here on the axis, the intercept, that's how fast we're going at time equals 0. So that's our initial velocity right there. The slope tells us our acceleration. So the slope here is 0, so the acceleration is 0. The slope here is positive, so we have a positive acceleration. And then if we had a negative slope, so say we had a graph that went this way, then that would be a negative acceleration. So a negative slope here has a corresponding downward curve parabola on the position time graph. A positive slope here on the velocity time graph, positive acceleration, has a corresponding upward parabola on the position time graph. There are a couple other things you can tell from a velocity time graph. If, say, you started up here, so say like your graph is up here, then that means that you have a positive velocity. If you're down here, you have a negative velocity. Okay? And then the last thing is that this area right here, say in this case between 0 and say 1-2 seconds, that would be our displacement. So if this was, say, 5 meters per second, then this area would be 5 times 2. That's the area bounded by that. And so that would be 10 meters. And so that means that we would have displaced 10 meters in the first 2 seconds. That means that this number up here would be 10 meters at 2 seconds. So that this corresponds. Sorry, my graph is getting really complicated. So this displacement, this is my delta x, this area. And you can take that between any 2 points depending on how you want to find, if you want to find out, say, like in this graph, if this is 0, 1, 2 seconds, and say again, let's make this 5 and 10, then say you wanted to find out how far we traveled between 1 and 2 seconds, then that would be this area right in here, and you would find that area. Now that's a weird shape, it's a trapezoid. If you don't remember the trapezoid rule, which we probably won't, that's okay. then all you have to do is break it into a rectangle down here and a triangle up top. So this rectangle down here has a side down here of 1 and a side over here of 5. So the area of this one is 5 meters because this is seconds and this is meters per second. So when we multiply them, we get 5 meters. This one right here, this upper one right here, that's a triangle, so it's 1/2 base times height. So instead of 5, this one's going to have an area of 2.5. So when you add those up, meters by the way, when you add those two up, that means it would have traveled 7.5 meters between 1 and 2 seconds. Okay? So that's how we find information on a velocity time graph. If we're above or below the axis, that means we're going forward or backwards. So this is forward, and this is backwards, or positive or negative direction. The initial velocity is right here on the axis. The area is the displacement. The slope is the acceleration. All right, so let's move on to our acceleration time graph. These two graphs are really simple. They're 0. But this right here, this spot tells us what our constant acceleration is. Okay? Okay, right there. That's our constant acceleration value. And since it's constant, you could read it off anywhere here. It doesn't matter. And the fact that it's flat tells us that the acceleration is constant. Now, on the AP test, we're likely to see graphs that will do something like this. Say we have an acceleration like this, and then the acceleration drops to 0, and and it may jump up, say up to this value. Okay, and the reason they do that is to make it easy for us non-calculus people to analyze the graphs. They're just saying that for the first second between here and here, we have a constant acceleration of, say, 1. Okay? And then for the next second, between 1 and 2 seconds, we have a 0 acceleration. And then for the last one, we have an acceleration of, say, 2 meters per second. So you just handle it piece by piece. So the first part of this graph will be a constant acceleration graph with an acceleration of 1. The second part of the graph will be a constant velocity, and the third part of the graph will be an acceleration again. All right, so you just handle it piece by piece if you get one like this. So let's look at some examples. So here's a great place for you to look. If you go right here to ophysics.com, there under kinematics, there is a bunch of different examples that you can look at. And here is one. So right here we see that we have this right here is a constant position or at rest object. The object can be at rest anywhere over here in the positive space or in the negative space. It doesn't matter. It's just telling you where it's located. So like this one's located at negative 2.3. All right, so constant position. It just sits there and the velocity is 0 and the acceleration is 0. Now, what happens when we add some velocity? So let's add some velocity here. Now I have a velocity of, in this case, 0.76 meters per second. And I have a starting position of 1.04. And then this slope right here has to be equal to 0.76 meters per second. We could start in the negative space. We could start in the positive space. It doesn't even matter. We're going to end up with the exact same slope. All right, now let's look at acceleration. What happens if we give it a positive acceleration? So now when this has a positive acceleration of 0.48, we have a starting velocity of 0.76, but then it has a slope upward because it's increasing in speed. So I want you to notice that since our acceleration is positive and our velocity is positive, we're getting faster and faster and faster. But if I have this start down here in the negative velocity area, so we start by going in the negative direction, but we have an acceleration in the positive direction. That means that we're going fast and we're slowing down to 0 here. So we stop right here, turn around, and then go in the positive direction because the acceleration is to the right, the velocity is to the left. We see this kind of thing, say like when we throw something into the air, the velocity initially is up, but the acceleration is down, so it slows down on the way up. Then it stops, then it turns around, and it comes down. And as it comes down, the velocity and the acceleration are in the same direction, so it speeds up. So let's match this graph with this graph. So we start with a slope here that's negative. That checks with our negative initial velocity. We have a zero slope here, and that's about at this third mark here, and we go over here, third mark, hey, we have a zero velocity right there. So the slope here should match the position, where the velocity is here. So the velocity here reads at 0. Okay? And you can play around with this. You can start this graph up and down wherever you want. You can change the initial velocity, and it changes the way the curve looks on the position time graph. Okay, so let's see if you get it. Let's practice. All right, so I want you to look at this right here. I want you to predict, based on this velocity time graph, what will the acceleration time graph look like and what will the position time graph look like. Ready, set, pause your video and sketch what you think they're going to look like. Unpause your video. Now take a look and see what we get. Let's see. So this has a zero velocity here. It starts going in the negative direction, slows down, stops, and then speeds up and goes in the positive direction. It has a positive acceleration, so I should have an acceleration across here. Since this slope is constant, the acceleration should be constant across here somewhere. So let's see. There we go. Perfect. All right, so now position time graph. This will be harder. So we start with a negative velocity. So therefore we start with a negative slope. Now I have it starting right here. So it's going to start downward. And then the velocity gets going to 0 eventually. So it should have a big slope here. It should have a 0 slope at this vertical marking right here. And then it should have a positive slope over here. So it should go down, and then it should stop, and then should go back up. And so it should be parabolic upward because we have a positive acceleration. And there we go. Perfect. Now, we could start this one at a different spot. It doesn't matter. We're going to end up with the same curve. Excellent. Okay, let's try another one. So let's get rid of these. I'm going to change this graph up to look like this. There we go. All right, so here's our new graph. I want you to take a look at this one. I want you to pause the video. I want you to sketch what will the acceleration time graph look like and what will the position time graph look like. And we're starting the position time graph at 0. Okay, ready, set, pause. Okay, now that you've had a chance to sketch what your predictions are, take a look and let's analyze these. So this is starting with a downward slope, so that means it has a negative acceleration to begin. And then we have, so we should go a negative acceleration, and that slope is constant, so it should be a negative value down here somewhere. And then we have a 0 acceleration here, so we should have a zero acceleration in this area, and then we have a positive acceleration here because it has a positive slope. Notice this positive slope is bigger than this downward negative slope, so the positive acceleration should be greater over here than it is over here negative. So let's see, and there we go. All right, stair-step graph. It's okay to draw these. I know your math teacher will get mad at you for drawing vertical lines, but we're just doing our approximation of what the graph's going to look like. All right, position time graph. This will be a little harder. So right here we have constant negative acceleration. That means we're going to have parabolic down. And then we're going to have 0 acceleration, constant negative velocity. So that means we're going to have a linear section downward with a negative slope. And then we have a positive acceleration, and so therefore we should have an upward curve. So let's see. oops, it's a little hard to see. We have a downward curve for the first two, and then linear, and then it looks like it's curving. I'm going to move this up so we can see it better. And there we go. Notice this curves down for two sections, and then it's linear in the middle, right here, and then it curves upward. And it's a tighter curve here because we have a bigger acceleration. Excellent. Okay, one more. So here's our acceleration versus time. So I have an acceleration time built like this. I want you to see if you can build what the velocity time and the position time will look like based on this graph. So ready, set, pause your video. All right, let's check to see how you did. So take a look here. This is a zero acceleration. So that means the velocity should be what? It has to have a slope of 0, right? So the slope here has to be 0, and we're starting at 0. So it should be 0, right? And then we go over here, and we have a negative acceleration. That means we should have a negative slope here, downward. And then we should have a acceleration of 0, which means there's 0 slope over here. So it should go over, down, and then over. And there we go. All right, now for the harder one. So this is a 0 acceleration, 0 velocity. So that means, what's this doing? It's doing like nothing, right? It should just be sitting still. This is not moving, not accelerating, so it should go straight across. And then right here, we have a negative acceleration. So it should be parabolic down, downward. And then we have no acceleration, but now we have a negative velocity, right? So it should be 0, parabolic down, and then this last section, that's a constant velocity, but it's negative, so it should be linear. So let's see. Son of a gun, we got it right. I'm going to move it up here so we can see a little better. So zero velocity here, an increasing negative velocity because it's negative acceleration, and then a constant linear negative velocity here. So like if I move this one up, notice what happens. I end up with a curve, parabolic part up, and I have a positive velocity here. Okay? All right, ladies and gentlemen, that's it. So congratulations, you're doing awesome, and we will do some practice problems next. Bye.